Deepak, whenever you want to start, you can start, okay?
Okay.
And when Amog is ready.
Yeah, so we will start now. Good evening, everyone. Welcome all to the second lecture of monthly research article spotlight. So today lecture is by Mr. Amoghavarsha or Kini. Amoghavarsha has completed masters in chemistry from University of Mysore, where he explored the synthesis and characterization of metal complexes. His research journey has taken him to prestigious institutions such as ISC Bangalore and IIT Madras, where he has been deeply involved in developing the advanced nanomaterial with the real-world application. Beyond research, Amoghavarsha has been an active participant in international conferences, workshops, and symposium and meetings, presenting his recent work. So today he will share his insights about his recent paper. Please join me welcoming Amoghavarsha Arkemi. So Amoghavarsha, floor is yours.
Thank you for that introduction, Deepak. Is my screen visible? Full screen?
Yes.
Yes.
Okay. I welcome you all to this talk. Today I'll be presenting the recent work I published in Chemistry of Materials, which is titled as Nanomechanical Investigations of Crystals of Copper Nanocluster Isomorphs, Enhanced Hardness of the Low Density Analog. This work is a collaborative venture between IIT Madras, where Professor Pichush Ghosh and Professor Pradeep is working, and JNCSR Bangalore, where Professor Umesh V. Wagmare is working, and Czech Republic Institute of Inorganic Chemistry, where Dr. Thomas Basse is present. Now, let us move on to the abstract of this paper, where I have shown everything we have done in the study. What we have done is we took copper 4 nanocluster protected by two different ligands. One is orthocarbonithiol and one is metacarbonithiol. And we have crystallized those two compounds. And we have indented the samples using nano indenter, from which we got data like this. And here we can briefly see that the pink trace showing the data for copper 4 OCBT shows that it is displacing a little less than copper 4 MCBT, that is the blue trace, for the same applied load, indicating copper 4 OCBT is slightly stronger. But the main point to notice here is the copper 4 OCBT, the density is slightly less than copper 4 MCBT, which whose values are shown here at the bottom of the samples. The normal notion is that harder material are the ones which have higher density, but we saw the opposite of it. So what we wanted to do was to explore more on this. So let me discuss the background of this study. So there are two papers on the detailed nanoindentation studies of nanocluster crystals, and both of them are from our group, that is Pradeep Research Group. And both of them were published by Dr. Sugi, and they have studied the nanoindentation or the mechanical properties of Ag29 nanoclusters and Ag40/46 nanoclusters, which are protected by organic thiols. And the interactions present between the clusters is either pi-pi stacking between the ligands, or the CH pi interactions in the intercluster space. Now, what we have done in our work is use an inorganic thiol. Is an inorganic thiol, and that is called as a carborane thiol, and which is different from these organic thiols, as we don't have pi interactions or CH pi interactions. We just have carbon hydrogen and boron hydrogen interactions. Now, what motivated us to do this study is to establish a structure property relationship in atomically precise metal nanoclusters. Because when we understand the structure property relationships, we can tune the structure to induce certain properties. And studying the mechanical property of a material is very much helpful, because whenever we study the mechanical property of a crystal, we can predict to which application it can be used for. And also the easy availability of the thermally robust and photoluminescent nanoclusters, which are protected by carborane thiol. The samples I am going to show you today are stable up to 350 degrees Celsius, and hence can be used in any nano devices which has applications in different verticals. Now, just briefly, everybody knows what nanocluster is, but just briefly, I'll show you the common slide which I show in every presentation. For that, I'll take two scales, that is dimension and age of a human being, dimension from angstrom to nanometer scale. Where I'd like to compare the molecules to a child which has high energy but low stability. By low stability, I mean that they are reactive to each and every stimuli in their environment. Similar to that, the molecules have high energy gaps between their energy levels, and also they are highly reactive to to their environments. Similarly, we can compare the nanoparticles to an old age man who has lesser energy but higher stability. It means that they have lower energy, but they have gained a lot of stability in their life because of long existence. Similar to that, nanoparticles will have low to no energy gaps because of the overlapping of the conduction and the valence bands, and also they are quite stable when compared to the molecules. Now, the nanocluster shines here because it is a good blend between high energy and also the greater stability, which shows stability similar to that of nanoparticles, and the energy gaps which are similar to that of molecules. And these energy gaps can be easily tuned to induce some properties to suit our needs for applications. Now, coming to the nano indentation technique, what is this technique? Let me quote Professor Piyush Ghosh, where in one of his lectures, he told that whenever we buy fruits, we first test if the fruit is ripe or not by pressing onto the fruit. When we feel that the fruit is soft, we buy the fruit because it is ripe. Similar to that, we first press into the sample and understand the property of that sample. That is what nano indentation is. But here the pressing is occurring in a nanometer scale. For that, we use a diamond tip, and the shape of tip can be different, like a spherical tip, conical tip, or any other tip. But this kind of tip is called as a Berkovich tip, which is very efficient to study the mechanical properties of molecular crystals, that is crystals of nanoclusters. Here we use a 400 nanometer diameter diamond tip, which is indented into the sample and taken out of the sample. And during this process, a transducer will study or read the changes in the load and displacement of the sample. That is shown here in the graph as load displacement curve. So here we can see whenever we indent the sample, the load goes on increasing and also the displacement goes on increasing. And once we reach a specified load, which we can change anytime, we give a little bit of holding time. Holding time is because whenever we indent a sample and remove it immediately, the sample will lag between the behind the tip, and we cannot get the accurate measurement of the properties, mechanical properties of the crystals. That's why a little bit of holding time is given and then unloaded. Whenever we unload, some of the deformations which occur can be recovered, and this is called as elastic recovery region. And the other region which cannot be recovered is called as a plastic region. And the slope of this unloading curve is what gives us the Young's modulus, hardness, and other mechanical properties of crystals. Now, what is this Young's modulus and hardness? So Young's modulus is the material's resistance to elastic deformation, whereas hardness is the material's deformation to plastic deformation. Simply to explain, I'll take two examples. One is a rubber band and one metal wire. If I take the rubber band, I can stretch the rubber band to whatever length I need, not too much, but I can stretch it, and when I leave it, it will come back to its original shape. So such a material is said to have very low Young's modulus, meaning it is very flexible and very less stiff. And in case of metal wire, we cannot stretch it as flexibly as rubber band, and also if we apply too much of pressure, it will break before stretching. So that is a material having high Young's modulus. Similarly, hardness is what we define as materials innate resistance to scratching or denting. So if I take the rubber band and I pinch it, I can see that I can put a dent in the rubber band easily. Whereas if I have to do the same for the metal wire, it is very difficult. So hardness is very high in case of metal wire compared to the rubber band. Then we do the time dependent properties called as stress relaxation and creep, which I'll explain, and also frequency dependent mechanical properties, which are called dynamic mechanical analysis. Now, directly jumping to the results and discussion, here I have shown how we have synthesized these nanoclusters. First, we have synthesized a phosphine protected copper 18 nanocluster, and to that we have added orthocarboranthiol and metacarboranthiol, both of which are differing only in the position of the carbon atom in the structure. They both form copper 4 nanocluster with a shape of the core like this. Each vertices is having one copper atom in it, and they are protected by ortho and metacarboranthials. Now, the only difference between these two cluster is again the position of the carbon atom in the ligand. Even then, they show varied properties, like the different properties compared to each other, and also they crystallize in different crystal systems, one being trigonal for copper 4 OCBT and monoclinic for copper 4 MCBT. Here we have to note that the density of copper 4 OCBT is around 1.428 gram per centimeter cube, whereas it is 1.442 for copper 4 MCBT, which is slightly higher than copper 4 OCBT. After this, we have done the phase indexing to understand which phase is available for indentation. For this, we have loaded the crystal onto the single crystal X-ray diffractometers and indexed all the phases. And we selected the phase 0, 0, -1 and 1, 0, 0, 0, -1 for copper 4 OCBT and 1, 0, 0 for copper 4 MCBT. We have selected these phases which are completely different from each other because as we can see here, the crystals are very thin and we could not manipulate the crystals to turn them and indent the other phases. Hence, we indented the phases which were naturally exposed after the crystal growth. When we observe the crystals packing along the direction perpendicular to the indentation direction, we see that in copper 4 OCBT, the clusters are arranged in A, B, C plane fashion, but the ligands are arranged along the slanted planes like this, and the interaction between, that is the intercluster interactions involved in these clusters are along these slanted planes and are not along these ABC planes. Whereas in the case of copper 4 MCBT, the clusters are arranged in AB fashion, and the interactions between the clusters also lie along these AB planes. This is the main difference, and this is what is giving rise to different mechanical properties which we observe in the next slides. So when we do the indentation, we just press into the sample and take out the tip. And two different techniques can be used. One is load controlled indentation on the left side and the displacement controlled indentation on the right side. One is the first one being load controlled. We specify the load and measure the change in displacement. And in displacement controlled, it is just the vice versa of it. Am I audible?
Yes, Amoghavarsha. Yeah.
Okay. Thank you. So now in the load control, we first specified 500 micronewtons of force and measured how much displacement is occurring into the sample. We can see that the pink trace indicating copper 4 OCBT, from this slide, all pink traces are for copper 4 OCBT and blue for copper 4 MCBT. We can see that copper 4 OCBT shows slightly lesser displacement when compared to copper 4 MCBT for the same applied load, indicating copper 4 OCBT is slightly stiffer or slightly stronger. Again, coming to displacement controlled indentation, we have specified a displacement of 300 nanometer, and we see that to attain the same displacement, copper 4 OCBT requires a large amount of force compared to copper 4 MCBT. Again, indicating copper 4 OCBT is slightly stronger than copper 4 MCBT. Now, we cannot arrive at this conclusion only by single measurement. So we have done multiple measurements at multiple different forces or pressures applied onto the sample, and also multiple different load functions. So the load function is the time required, time we give for loading, holding, and then unloading of the indenter tip into the sample. So for that, we have done in 500, 1000 and 5000 micronewtons of force. And we can see that all the data are converging to a point very near to each other. That means the data are repeatable. And from these, each unloading curve, we have extracted the Young's modulus and hardness value, which we have plotted as a distribution curve to obtain the Young's modulus and hardness values as shown here. Again, the values are higher for copper 4 OCBT being 9.79 and 8.54 gigapascal for copper 4 MCBT. Again, the hardness also follows the same trend. Then we went on to do the time-dependent mechanical properties in this crystals. As I mentioned earlier, whenever we indent the sample, we give a little time for loading, holding, and unloading. But in time-dependent measurements, what we do is we indent the sample in 1 second. That is what is shown here in this sudden increase in the displacement. And then we hold the tip inside the sample for 30 seconds to observe the changes in load or displacement. If we are observing the changes in displacement, it is called as creep measurement. And here we can see after the initial indentation, there is no change in displacement for up to 30 seconds, indicating that my material is strong and is stable under constant stress. So if you would have taken some polymer or other concrete-like materials, it would have shown the primary creep like this, and then went on to show secondary creep and tertiary creep, as I'm showing here through laser. It will show peaks like that or displacements like that. That is not a good material to hold. I mean, it is not a good material for structural components in some nano devices. Now coming to the stress relaxation curve, here we observe the changes in load after indenting the sample in 1 second. For up to 30 seconds, we observe the changes in load. We can see that the load is going on decreasing with time, indicating that under constant load, my material is slowly relieving the stress which is falling upon it. So my material is stable under constant stress, and also it is relieving the stress which is falling upon it. So this is a good material to use as a structural component for certain precision measuring instruments or some mechanical instruments, and also some crystal optics, etc. Then coming to dynamic mechanical analysis. So the measurements which we have done until now is just indenting the sample and then taking out the tip without any vibrations given to the tip. So this is called as a quasi-static measurement. But in this one, we are doing dynamic mechanical analysis, where we provide a certain frequency to the tip, where we are measured from 10 hertz to up to 220 hertz. And we get like the storage modulus and loss modulus values. The storage modulus and loss modulus, to define it, first the storage modulus is the amount of energy stored within the crystal when we apply the force, and the loss modulus is the amount of energy lost from the crystal due to acoustic vibrations or thermal vibrations, etc. Now we can see the storage modulus is quite high and is frequency independent in both the samples, and is quite similar to the reduced Young's modulus for copper 4 MCBT and slightly higher in case of copper 4 OCBT. This indicates that my material is showing frequency independent storage modulus. And in case of loss modulus, the loss modulus is quite low compared to the storage modulus. And it is showing slight frequency dependency only because the scale is very small when compared to the storage modulus. But this we can tell as frequency independent, but very low loss modulus. Now, such materials can be used as mechanical resonators, where they store energy and they don't lose much of the energy which is stored within it. And this energy can then be used for other sources. Like if we take pendulum, if a pendulum is moving or swaying, then it will be, when under motion, it will be showing the kinetic energy. But at 2 points on the extreme left and right, at certain time, for a small amount of time, it will be at rest. That will be the potential energy. So it is converting the potential energy to kinetic energy. Similar to that, these materials can be used as mechanical resonators, and also they can be used in vibration damping applications. Now, we also tried to compute this property to understand why it is behaving like this. As we saw that the copper 4 OCBT has lesser density, even then it is showing higher strength. So for that, we took the sample and we applied 1% and 2% strain onto the structure on both positive and negative side. So we now have 4 strained structures. Then we did not allow the strained structures to relax. And we measured the Young's modulus of that, which is called as E bare, which I'll show in the next slide. Then we allowed these 4 structures to relax. And we got the Young's modulus values of 12.9 for copper 4 OCBT and 10.1 for copper 4 MCBT. Now, the linearity of this graph indicates that as we apply the strain, the stress falling upon the crystal is following the Hooke's law. And in case of this values, also we can see that copper 4 OCBT is showing slightly more stress upon its structure than copper 4 MCBT. To summarize this computational study, the E bare, which I defined as the Young's modulus of unrelaxed structure, we can see that the Young's modulus is 232 gigapascal for copper 4 OCBT and 234 gigapascal for copper 4 MCBT, which is following the normal trend that highly dense material is having a higher hardness or higher Young's modulus. But when we allow the structure to relax, there are certain mechanisms of relaxing in both of the clusters which is different from each other. That is giving the observed mechanical properties, which can be also seen in computation, where we get 12.9 gigapascal for copper 4 OCBT and 10.1 gigapascal of Young's modulus for copper 4 MCBT. These values are quite high when compared to experimental values, but they follow the same trend that the lesser dense material is having higher Young's modulus. These are just DFT calculated densities. Now, coming to the conclusion of my work, despite their closely related molecular structures, copper 4 nanoclusters protected by orthocarboranthiol exhibit superior rigidity and hardness compared to their metacarboranthiol isomeric analog. Then our findings indicate the critical role played by orientation of lattice planes relative to the direction of the applied load and the interactions among clusters in determining the observed mechanical properties. Then our material also shows high temperature stability, as I mentioned earlier. It is stable up to 350 degrees Celsius, and such materials can be used in various applications like crystal optics, precision measurement instruments, mechanical resonators, and nanomechanical instruments as structural components, and also in vibration damping applications. Now in future direction, we can observe the changes in mechanical property with the temperature, which we are already doing. Then exploring more crystals of metal nanocluster to create a library of mechanical properties and their probable applications. As I told, studying mechanical properties will enable us to understand where these materials can be applied. And also exploring the structure property relationship with advanced characterization tools like microED, which we have now for structure determination. And it is very powerful to study the solvents which are included within the crystals and also nano indentation with in situ single crystal XRD. One of the reviewers for this work asked if I can probe the changes in the structure of nanocluster where we have indented, but that requires a sophisticated instrument which has a single crystal XRD in situ that we don't have. But if we have that, it is very good for our nano indentation studies. and also more computational studies to understand what is happening within the crystal under the stress. Then coming to my last slide, I would like to thank my guide, Professor T. Pradeep, for giving me an opportunity to present here in this platform. And my collaborators, Professor Piyush Ghosh, who has helped me in the nano indentation studies. He's from IIT Madras. And Dr. Thomas Basse, who has supplied us with orthocarborane and metacarborane thiol ligands. And Professor Umesh Wagmare, who has done all the computational studies. My institute, IIT Madras, and DST and CSR for their funding. And my group and all of the listeners here for listening to my talk. Thank you.
Thank you, Amoghavarsha, for very interesting talk and discussing about your work. So the floor is now open for the question and discussion. Please ask question if you have any.
Yeah, Amog, nice talk as usual. So
Thank you,
yeah,
Professor.
fantastic work basically. So I was having just one query. So
Yeah.
how good this material is in comparison to typical copper complex or copper crystals which are known, or is there any other study related to just copper complex or whichever is crystallized so far, not clustered? I just wanted to like have a idea. So do you have any reference for that, like in compared to those materials, how good they are, our clusters are?
Okay, copper complexes I have not come across till now, but metal complexes usually they have different kinds of ligands which have different kinds of interactions. Even then, if we take the copper complexes, they usually have organic thiols. And in background study, I showed these Ag29 clusters which also use organic thiols. They have pi stacking and all, but their strength is in the range of 3 to 5 gigapascal only. But this copper nanocluster, which is protected by carborane thiol, is showing higher strength. Mainly, we think is because of the rigid carborane cage, which is protecting the metal, and also the very small size of the cluster as well. So we are probing other nanoclusters as well, which are protected by carborane thiol. We have synthesized Ag14 and we have done the nano indentation studies as well. They also are showing high Young's modulus and hardness values when compared to the organic thiol counterparts. So maybe I don't know about the literature which is present now, but I can hypothesize that clusters with these carborane thiol are better materials than their complex counterparts.
Okay.
That's what
Okay.
I can hypothesize now.
Yeah. This is probably this is what also I think so. But we
Yes.
need to do a lot of studies. This is what basically what you are
Yes.
currently doing. A library of
Yes, sir.
materials need to be studied. Yeah. Okay. Thank you,
Yes,
Amog.
Thank you. Thank you.
Let me just add one more thing. So regarding this hardness and high young moduli, so this carbon itself have the young moduli, elastic young modulus around 9 gigapascal. So itself a carbon alone without the metals. So
Yes.
carbon is quite hard, and also like not hard, like it's having the plastic in nature as well as being the high elastic modulus. So
High
one study
elastic modulus and plastic in nature.
yeah, plastic in nature. So recently I was doing this for the O9 alone, doing the like when I was trying to understand this is like very plastic. Hardness is around 95 megapascal, very low.
95
Yeah,
megapascal hardness. That
yeah,
is quite low, right?
yeah. That's why this is behaving as a plastic. The O9
So now we
itself.
can again one thing we can arrive at, like if you can share that with me, we can see
Yes.
that the gigapascal for the Young's modulus is similar to what we have observed is what you are saying,
Yeah,
but the hardness is quite low.
yeah,
So that means that one of the properties is through the metal core and one of the properties may be because of the ligand.
yeah. That's
So
correct.
this is an interesting thing. We can compare this with whatever the data you have, and we can discuss on this. That's interesting actually.
And I have one question, like why you did this depth dependent study? What was the purpose of doing the depth dependent nano indentation?
Depth dependent meaning
Yeah,
you are asking for
yeah,
this one?
yes. So
Okay,
what was
see,
the purpose?
whenever we specify a certain load, we do it for 500 to very maximum load up to which the material can sustain. But we can also specify the displacement to study how much load it takes for that displacement to undergo. Like if what can I say? If you have some applications where certain depth without fracturing the material, you want to insert your some cantilever into the certain depth without fracturing the material. So we need to know where the material fractures. If there is a fracture, these arrows I am showing is called as pop-ins. But if there is a fracture, these pop-ins will be very pronounced, very high, and there is sudden jump in the load. So that can be observed through displacement dependent studies as well. Only load dependent will give us like this, where the depth is not specified and depth can be different for different places where we indent. But for depth dependent studies, the depth is always constant, but their load that they can take, we can understand the range of load the material takes to attain that depth. Did you understand?
Yes. So another question, like the indentation is directionally dependent, so you have to
Yes.
understand each direction of this one.
Yes.
So while the computation, have you probe for the different possible direction, and what
No,
are the you
actually,
see some difference in different direction?
we should see some difference because the crystals are anisotropic, and indentation of anisotropic crystals have shown direction dependent properties, example in caffeine and omeprazole crystals. But we did not do computationally because it was computationally expensive, and this computation alone took us around 5 to 6 months. So we did not probe into it much. But as I mentioned, in the future direction, we have to probe into this direction dependent properties more.
Is this computation done by Vespa? Vespa
Yes,
software?
Vespa, and I mean not Vespa, VASP actually, Vienna
Ah,
ab initio simulation package, and also we have used Purdue Burke Zeroff method, and also the PAW method, which is called as the augmented wave method. I'm not sure about that, but that's what we have used to understand the electron densities and also the change in forces and movement of molecules.
okay, thank you.
Yep. Thank you.
Amog Bhaiya, I have just a small
Yes.
doubt.
Yes.
Like how we are deciding which plane to choose for nano indentation, like if there is any specific criteria that we have to choose this
No,
plane.
no, there is no criteria here. The criteria for me was it was easier to indent the plane which was already exposed after crystal growth. There is no criteria to choose. Each and every plane of the crystal you can indent if it is easier for you to indent it. So here 100 for copper 4 MCBT and 00 -1 was easier because this hexagonal plane you see is large enough, but other planes which you can see here are very small. We cannot make the crystal stand like this and indent without getting a lot of errors. That's why we
And
chose these planes.
Amogha,
and
I have one idea. Like, so your
Yes.
this copper ore is very high luminescent, right?
Yes.
So when you are doing the indentation, you are basically disturbing the surrounding of the system. So is it
Yes.
possible to probe the with the confocal something like PL to see the PL versus load? Like how much your
PL
load?
versus load. Yes, that is an interesting technique. Professor Piyush was also discussing. You were also there in that. So if we can indent the sample and we can study only that point of indentation, because the indentation is occurring in nanometer range. Right. So only that point should be focused to understand the change in photoluminescence. If you get some background photoluminescence from the regions which are not indented, then it will be like it will not give us any changes than the normal measurements. So the precise measurements are very much required to understand that. Even that for single crystal XRD measurements, which I told in the future direction also requires we have to probe the X-ray onto that point and study the changes in the structure at that point
But
under the tip of indenter.
doing the X-rays, from my understanding, is not possible because the
Not
even
possible. Yes.
micro focus X-ray will be 150 micrometer size,
Yes.
and
Yes.
your
We cannot
indentation
do
is
it easily.
very small.
Correct.
Yeah.
Among Bhaiya,
Yes.
regarding the planes, if you indent on the 0, 0, -1 plane of the copper MCBT cluster crystal, will the indentation behavior will be same? Can we compare like this?
No, that's what I told. Crystals are anisotropic, right? So anisotropic crystals will have different properties along different directions.
Yeah, so the strength also can change if we indent along the 0,
Strength
0,
strength can change, but the relaxation behavior is what matters for the Young's modulus and hardness values. So Young's modulus and hardness values won't change much of the property, because as I showed in this, the slope of unloading curve where the material is relaxing is what gives us the property of the material, and not this one, not the loading curve.
Okay.
So
Because
whenever
we
you are putting
compare,
pressure along different faces may have different way to let the tip inside the material, but when they relax, the material relaxes in much like complex ways, like acoustic vibrations are possible, thermal vibrations, then rotation of ligand. In this paper itself, I have shown that copper for OCBT, the ligands rotate like this, and when they relax, they come back like this. But in case of copper for MCBT, the whole cluster compresses and then expands. That is what we have shown through computation. So that relaxation method can be slightly different when compared to direction dependent, but not much different when we get the Young's modulus and hardness values.
So, Amogha, so continuing your the answer, like since you are saying this small difference, like big differences in the, but you are comparing the two different planes.
Yes.
And you have not compared with the computationally about the same plane. Like what are the Young moduli for the same plane
Yes.
theoretically, whether it was same or
Yes.
different.
So for that, I can answer that this whatever the moduli we get for a material is the bulk, is comparable to the bulk modulus as well. Did you understand? Like the whole material, actually you can even test it in your in our lab itself without measuring it. Take a spatula and just put some pressure on both copper for OCBT and MCBT crystals. You can see that copper for OCBT is slightly difficult to break than the copper for MCBT crystals. That we have seen after measuring this also. So that like bulk modulus is similar to what we do from nano indentation. Even when we indent a nanometer region, there is a, let me just show you. So even if I indent a small region like this, this triangle being the indentation, below the crystal, like if I indent here, below the crystal, there is a region of plastic zone, which is extending into the bulk of the crystal. There also the movement has occurred within the crystal, but we are only indenting the top of it. So whatever the property or whatever the relaxation is occurring is coming from the bulk itself.
Yeah, there are some paper regarding this on the MD
Yes.
simulation.
Yes.
But still, I am concerned about like when you are comparing, it should be the same plane. Even not, if you are not able to access the same plane by experiment, you should compare with the theoretical at least.
Yeah, we should have done that, but as I told, it was taking a lot of time for, and also it was computationally expensive.
Okay.
But we are
Thank
trying
you.
to do that with Ag14 crystals, I think.
Thank you.
Okay, thank you.
Among Bhaiya, you did the
Yes.
creep behavior as a function of time of the crystals.
Yes.
And
Yes.
for only 30 seconds, right?
Yes.
So what is happening beyond 30 seconds? And you told that the crystals resist continuous deformation and stable.
Yes. Yes.
So is it
So
sufficient to compare 30 seconds?
yes, sufficient for molecular crystals, because we are applying a large amount of force into a small tip. So you understand what immense pressure is falling on it. So whenever you use it in a device, the whole crystal may be under pressure, but here you are putting whole crystal may be under pressure, and the pressure over the area will be quite less compared to the pressure which we are applying here. Even when the force applied is 500 micronewton, you have to understand that area which is applied is 400 nanometer. Now you have to understand what amount of pressure is falling on it. And we have applied that pressure in 1 second, and we are holding it there. So that immense pressure is falling on the crystal. Even then, it is not showing any extra secondary and tertiary creep. That is what is understood from this, and it is normal. It is a normal protocol for indentation to be done and held it for 30 seconds.
Okay.
So we have held it for more than 30 seconds as well, and it is not showing any creep behavior.
I have one query.
Yes.
Now you are having two different carbon thiols. Both of them are
Yes.
isomers. So
Yes.
if it is some different substituents on that carbon, can you predict some pattern in this hardness and elasticity, such as some dithiol or some bulkier substitutions? Because if you
Yes,
can
that-
predict it, then based on that you can synthesize that materials which can be of more harder.
Yes, yes, that is actually a great topic. Like if dithiol is there, the material will be more rigidly attached to the cluster. And if some extra, like if we have a thiol one side and a COH on other side, there will be hydrogen bonding possibilities as well with another COH from another ligand. Again, the interactions between the cluster is different. So their property may be slightly stronger than that of these normal carborane thiols. So predictive study, I think we have to build a library first with multiple different samples so that we can understand all the different parameters which are affecting the mechanical properties. But I think we can predict that once we have enough data to predict such things.
Okay.
Yeah, I want to know,
Yes.
in your 10th slide, can you please go to that?
Yes.
Yeah, in your A figure, what does this represent at the left top and the right bottom?
Sorry, I did
I'm
not
not able to
mention
see.
that.
Yes.
Yeah, so the copper for OCBT I have shown here as clusters are arranged in the plane and their ligands are arranged in slanted layers. Whereas in MCBT, clusters are also arranged in the plane and ligands are also, and interactions are also occurring in the same plane, right? That is what I have shown it here schematically. While while I was writing paper, it was suggested to me to, I had mixed these two figures and had put it as one figure, but it was suggested to me to separate it out. So while reading the paper, it is difficult to go back to that figure and get the plane again, see the plane. That's why I put a schematic here to indicate copper for OCBT as clusters on the same plane and ligands along the slanted planes, and MCBT on the same plane. That's all.
Okay, thank you.
Okay.
Amog, I
Priyanka
have
had some.
just
Yes.
a small doubt.
Yeah.
Like
Yeah.
after loading and deloading, after like the
Yeah,
reloading
yeah.
is done, how do you know that the planes have not collapsed or the crystal is stable like that?
Yes, that's a very good question. So here you can see the arrows which are here indicating that there is sudden change in displacement when we are loading the crystal. These are called as pop-ins, meaning the plane is giving away and it is resisting to the maximum possible strength. But after that, it gives away to the tip and the tip will suddenly go inside. That is shown in pop-ins. But if there is a material failure, if the material completely breaks, then the tip load will be same, but the displacement will be very large. So you can see in this diagram, which I have exaggerated this pop-in. So this is also a pop-in, but if I can extend it to a higher displacement, then we can know that the material has completely failed to sustain the load. That is how we can
When
understand.
it is deloading also, will you see that pop?
Yes, those are called as pop-outs. And while pop-outs are not usually seen, these can occur like this. Sudden decrease in displacement can also occur because if the material crumples down, it can put a pressure on the tip. Hence, displacement will suddenly go on decreasing.
Say in your
Pop-outs
plot,
can also occur.
we can only see pop in and not pop out, right? In your data.
No. In my case, yes.
So does it mean that the planes are not coming back?
No. Planes are coming back because the indentation shows. 1 minute. The indentation shows slight amount of recovery, right?
Okay.
This is the maximum displacement and there is recovery. This is the at the end, displacement at the end. But what it means that pop out is not there, meaning there is no damage to the sample while we are unloading.
Okay.
Whatever deformation I gave during loading is sustaining and some amount is recovered.
Okay, and one more thing. If
Yes.
say your clusters are arranged in a directional manner by metal or ligand, how good will your data look? Because you are saying this is not directional, that's why this is not like great. But if it will be directional, say you assemble them.
Like you get a cubic crystal where it's an isotropic crystal. Are you telling like
If you
that?
get an isotropic, how good
Okay.
your data will be?
So in isotropic crystals, all it's like not good or bad data. I would seem whatever the data we get would be this almost same or not almost same. It will be same for all the phases which we indent in a cubic crystal.
Okay, that's
So
your
that
take.
is what I think. Yeah, it's an isotropic crystal.
Let me clarify one thing here. For the higher symmetry, this young moduli will be mostly the low. So when you are comparing with the QB and the triclinic will have definitely the higher young moduli compared to the cubic.
That again comes question, right? Triclinic, it is not symmetrical and it is not
Yeah.
isotropic.
Yes, that's what
So you have to indent all the phases to like if you have to compare different crystal systems also, we have to do that. So we cannot generalize, I think.
No, it's a general. I was discussing about this mechanical computational. So they said like for the bulk, those who are computing for the bulk, like some ceramic and
okay.
all those. So they consider in which system it is, like a triclinic, monoclinic, hexagonal. Based on that, they compare like, okay, this system will have the higher young moduli and this will be have the lesser. So based on the crystal system, they compare, not based on the this like what you are
See, it
saying.
also depends on the property and relaxation of the material as well, because if you take, you told the one with higher symmetry has higher Young's modulus, right?
No, higher symmetry will have always the low.
Low, okay.
Yeah.
If you take a cubic crystal, which is of like if you consider metals are arranged in complete metals are arranged in cubic system, and my crystal is arranged in orthorhombic, obviously the metal will have higher Young's modulus. We cannot generalize based only on the system. We
No,
also
I'm
have to
telling
take
about
into account the molecular property, right?
I'm telling about the similar kind of system, not like you
Okay,
cannot
okay.
compare the metal with non-metal.
Yeah. Okay, I did not know about this, but I'll check it.
Yeah.
Thank you.
I guess what you were mentioning, it's about the packing efficiency, because itself for cubic system, you will have some packing efficiency. Means in the crystal system itself, in a single crystal, you will have more atoms, which will have more interaction maybe. So
okay,
if you want to generalize, that means in certain systems with certain crystals, the packing efficiency will change and hence the hardness will also change. If you want to talk about in a layman's language, if you just get rid of the atoms, what kind of atoms are there, what are the ligands and all those stuff.
Probably true. I'm not sure. I cannot comment. I have no idea on this, but I'll read it and get back to you.
Amog, you presented it very well.
Thank you, sir.
A couple of questions or concerns that I have.
Yes, sir.
Before that, let me first comment on Deepak's Young modulus. It is Young's modulus.
Yes.
It is Young's modulus, and because of Thomas Young, who proposed this kind of thing in 1807. Okay, Young's modulus. So now question is, one of the reasons why we are doing this kind of studies is to relate mechanical properties with properties of crystals.
Yes.
For example, this whole idea of mechanical properties of molecular crystals came into attention because this can be related to solubility. This can be of importance in characterizing pharmaceutically relevant molecules.
Yes.
And this is how this area got attention. That molecular crystals, why at all we should study? Otherwise, people were studying only metals and alloys.
Yes.
And they are obviously important things to study. So this studied because of the correlation between mechanical properties and the functions. So as far as CU4 system or cluster system is concerned, the very first paper on this said that, well, you have stimuli, right? Stimuli and functions. The correlation between this was what was Arijit's paper. Carborane thiol protected copper clusters, stimuli responsive materials.
Yes, yes, sir.
The property that was studied was luminescence or phosphorescence.
Yes.
So my question is, what is the relation between the mechanical properties and the stimuli responsive behavior of these materials? Now, obviously, you crack it, crush it, it gives you different luminescence, is what was said.
Yes, sir.
Can you relate it? Or is it all possible?
Sir, it is possible, as Deepak had suggested, like we can do the photoluminescence study on focusing only on the place where we indent, or also we can do what happens under pressure. We can do it under diamond anvil cell, but I think that would not.
So you see, some of these, one material, it is, let us say, supposed to be hard, but it is not hard.
Yes.
Now, is there a connection to its photoluminescence? Was it higher in intensity, lower in intensity? Did it show greater milling-induced luminescence?
Yes, sir. We have to probe into this. I'm not sure about this.
Yes. Okay. So this is one thing. But if, let us say, this is not directly correlated.
Yes, sir.
I am coming to Indranath's question. Let us say if you have a collection of these cluster systems.
Yes.
And several such mechanical properties are studied. So, is there some correlation that we can make? Say, relate that. You see, at this point in time, the cluster science is advancing. We still don't know whether there is a cluster which can actually melt. You know, a cluster crystal which can melt. Melting point of cluster crystals. See?
Yes, sir.
It's an interesting topic. Now, this can be related to mechanical property. Yeah? Because as Deepak was talking about, something that is lighter would probably melt earlier. It's essentially to say that the intercluster or intermolecular interactions are weaker. So stronger interactions will take higher temperature for it to melt. So there is probably materials, one function, one property can be related. Maybe another property could be conductivity. This kind of another property could be thermal conductivity.
Yes, sir.
So if you're strongly connected, it will more easily conduct heat.
Yes.
So like that, can we think of this could be another future direction that at some point in time someone can look at?
Yes, sir.
Okay, I would leave. Yeah.
This is a great great project, but we would need a lot of data points to correlate mechanical properties to certain other properties as well. Because sometimes it may be related, and sometimes it may also be not related to the mechanical property of the crystal as well. So whatever applications we proposed are based on structures, optics, etc. But the main photoluminescence property which we observe in almost all the clusters, and conductivity or thermal conductivity, we have to probe it. And one of the papers was there where they put the crystals of gold nanocluster inside a diamond anvil cell, and they measured the conductivity of these crystals under stress. That way, they told that under stress they are conducting more. That is because they are coming closer. But that way we can make if we make a library of materials with mechanical properties and their other properties, we can think of such things.
Absolutely. It just, there are numerous parameters
Yes.
which are relevant here when you start comparing mechanical properties and size, for example. Size is what? I mean, size is many parameters there, right? You can't
Yes.
have just merely change of size. So shape also changes.
Yes, sir.
Shape is changing all right, but ligand is changing. Ligand is changing, crystal structure is changing. So there are many different things. And so I agree with you that a
Yes, sir.
whole range of data are required.
Yes, sir.
Nevertheless, the whole idea of studying mechanical properties is to relate to functions.
Yes, sir.
And that's where we or the subject area has to expand to.
Correct.
I leave it there. You have presented it extremely well. There is absolutely no doubt that your capacity to present things is being increasingly evident, being enhanced in the course of time. Yeah. If at all you have to improve this data, how would you improve this?
Sir, the main thing everybody is asking is the different planes. If I can probe, I would use that to enhance this study. And the second main thing would be to get better quality crystals as well, sir, because I have a good data set, but I had to reject multiple data sets because there are different kinds of roughness on the surface which did not give us better data. So sometimes I had to discard some of the data which did not agree with our this one, and also solvent inclusions also inside the crystal. So we have to understand how to get better crystals in these nanoclusters. Nanocluster crystallization is quite difficult, I know, but there has to be some parameters. Like in organic chemistry, we do just evaporating the solvent from a pure compound will give us good crystals. I have seen here we have grown like 2 to 3 cube crystals which are very large in size, but that is never possible in nanocluster. Not possible now in nanocluster, but it's better if we can understand how crystallization occurs in nanocluster and how we can make it better, so that we can study their properties, not only mechanical but others, using better crystals. That would be my take.
Thank you. I think we'll have to close here. There's another meeting that is coming up at 7 o'clock. Deepak, can you please take it forward?
Yes. So thank you. There any other question?
Yeah, Amog, really
Yes,
nice
sir.
presentation or everything. So people has from our lab we have done silver AG29, Dr. Shugir, and
Yes.
then you have done copper, right?
Yes.
Then what about gold and alloy? You take both, right? So we'll have at least 7-8 data set, right? We have multiple this alloy and
Yes,
gold
but
also, yeah.
But 7-8 data sets of unique samples which we cannot compare with each other. So we need data sets which we can compare with each other. Example, AU25 nanocluster protected with different kinds of ligands. Same AU25, or AG29 nanocluster protected by adamantane and BDT. Similar on lipoic acid is also there, I think. So if we can get data sets of these, and then we can deduce this one. If I have silver now 2 to 3 data sets, and copper 1 data set, 2 data sets, and gold 3-4 data sets, I cannot compare them to get proper this one.
But that will be also interesting study. I don't know
Yes,
if
yes,
there
we have
with this
to.
ligand any complex or not. But if we make the complex, and because that whatever the first question asked by Dr. Indra, yeah, so that
Yes,
will be
yes.
really interesting. That we will have the structure of the already of the ligand, we have the structure of the cluster, we have the structure of the complex, right?
Complex,
So that
yes.
kind of is the, will be I think that will be,
We will have to
yeah.
close it now for something else that is there.
Yes, sir.
Thank you, Amoghavarsha, for very nice
Thank you.
and meaningful discussion on this.
Thank you.
So we will close this one, and the next lecture will be in March. I will send you the email, and next will be for the Tanmaya will present about her work, which recently she have published. I will send the email. Okay.
Thank you. Thank you.
Thank you.
Thank you, Amog. Thank you.
Thank you, sir.
Thank you, everyone, for joining.